Hey, welcome back. In this video, we're going to go back to probability. Specifically, we're going to look at random variables, discrete ones in particular, and we're going to look at expectations. This video might seem out of place, but these tools, random variables, expectations, and other tools from probability are very useful for proving bounds for extremal problems in combinatorics. So to start with, let's look at what is a random variable. So a random variable is a number that's assigned to each outcome of a random experiment. So let's look at some examples of random variables. So we could do this experiment where we flip a coin 5 times and look at how many heads in these 5 flips. And the random variable here is the number of heads. And that's in the total 5 flips. And we can look at another experiment. You roll 2 dice, and what is the sum of the numbers on top of the dice? And dice, I'm talking about standard dice with the numbers 1, 2, 3, 4, 5, 6. And the dice, they don't have numbers, they have dots on them. But when I say number, I mean the number of dots. So I'm using the numbers as a shorthand for number of dots. So our random variable there is just the sum of the numbers of dots on the top of the 2 dice. Another random variable we could look at, we can define it by choosing some point in the square. The square has corners at the origin, and it's a unit square. Its axis parallel. And we choose a point in the square, and we can ask, what is the x-coordinate? So our random variable here could just be the x-coordinate of the point. So these give us 3 different random variables. We're going to focus on a specific kind of random variable because this is the kind that we're going to be using for combinatorics problems. And that's a discrete random variable. And discrete random variables have countably many possible values. So for something to be countable, there's 2 possibilities. It can be finite. And when we're saying something's countable, we're talking about some set. So you can write it as x equals x1, x2. So it can be finite. In that case, we're talking about some set x1, x2, up to xk for some integer k. And it could be infinite, but in bijection, with the natural numbers. And natural numbers, recall, they are the non-negative integers, all of them. So in the case that they're infinite but in bijection with the natural numbers, it means that there exists some map f from x to the natural numbers, and this map must be a bijection. And the way that we've written our elements of x over here, an easy bijection we can define based on these labels is the bijection f of xi equals I minus 1. And it's easy to check that that's a bijection. We can define an inverse, f inverse of I, for each natural number I to be x of I plus 1. And I'll let you check that those maps are inverses of each other. And f inverse goes from the natural numbers to x. And that's assuming that this list x1, x2, and so on is infinite. So if it is infinite, we say that it's countable if we have this bijection. So something being countable, it can be finite or it can be infinite. But if it is infinite, it must be in bijection with the natural numbers. And being in bijection with the natural numbers, that just means that we can list it like we list the natural numbers, like x1, x2, x3, x4, and so on. So we can look at these three random variables up here, and we can ask which of these are discrete. So the first one, that random variable, we flip a coin 5 times. What's the total number of heads in those 5 flips? The possible values for the number of heads, we have 0 up to 5. So there's finitely many possible values. So that's countable. So this one is discrete. The second one, we roll 2 dice. What is the sum of the numbers on top? So the smallest possible number is 1 on each of the dice. The largest possible number is 6. So the sum of the numbers has to be at least 2. It must be at most 12. And it can be anything in between. So we have finitely many values again. So that one is also countable, and it's a discrete random variable. This last one, the x-coordinate of p, this x-coordinate can take any value in the interval from 0 to 1. If we assume that the point is in the interior of the square, then we can make that an open interval, so it doesn't include the 0 or 1. And this interval is uncountable. You cannot put it in bijection with the natural numbers, and there are clearly infinitely many numbers in that interval. like all of the positive powers of 1/2, for example. So it's infinite, but it's not countable. You cannot put it in bijection with the natural numbers. So that's example of one that is not discrete. So let's look at an example. Suppose that I roll 2 dice. Well, suppose they're fair, so they don't have some kind of weights that make them more likely to land on one side than another. We'll define a random variable, x. This will just be the sum of the numbers on the top of the dice. So remember, numbers here, shorthand for number of dots. And the dice, the numbers on the dice are 1, 2, 3, 4, 5, 6. So we can ask, what's the probability that this random variable x equals 7? And we can do this like we were doing probability problems before. So we can look at the universe of outcomes, and that's going to consist of ordered pairs. We'll say ordered pairs A comma B. A will be the number on the first, and B will be the number on the second dice. So each of these numbers, each of them is number of dots. And this A is going to be some number from 1 to 6. And same with the B. And we can look at this, the way that we have defined these outcomes, A comma B. All of the outcomes are equally likely. And we have 6 outcomes for A and 6 outcomes for B. So the number of outcomes we have for A comma B, there's going to be 36 total. And all of them are equally likely because all of them occur with probability 1 over 36. And when the outcomes are equally likely, we can calculate the probability that x equals 7 as the number of outcomes where x equals 7 divided by the total number of outcomes. And we said the total was 36. And the outcomes where we get 7, they're pretty easy to list. We can list them. We get a 1 and a 6, a 2 and a 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. And we see there's 6 of them. So we get 6 over 36, and this gives us 1/6. So here's a problem for you to think about. What's the probability that this random variable x equals 6? Let's look at another example. Suppose instead of dice that I have a coin. It's a fair coin. It's not weighted. And I flip it 5 times. And I define a random variable again. We'll give it the same name as last time. X will be the number of heads total in these 5 flips. So we can ask, what's the probability that this x equals 2? So this time we can also define some outcomes that are equally likely. Our universe of outcomes will be 5 tuples this time. We'll name the entries A, B, C, D, E, the variables for the entries. Each of these variables, A, B, C, D, E, can be heads or tails. We have a total here of 32 outcomes. And each outcome occurs with probability 1 over 32. It's 1/2 to the 5th. So all the outcomes are equally likely, and we can do the same type of calculation that we did last time. So we can count the number of outcomes where x equals 2. So outcomes where we get a total of 2 heads out of the 5 flips, and divide that by the total number of outcomes. So we already know the total number of outcomes is 32. Outcomes with 2 heads, we could list them all if we wanted to. We could write like head, head, tail, 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 head, tail, head, tail, tail, dot, dot, dot. If we really wanted to, we could do that. But a better way to do it is we can count the number of ways to permute this one. So it's going to be permutations with repeats, what we did in that video. 5 factorial divided by 2 factorial times 3 factorial. Because we have 2 h's, 2 of them, and 3 of the t's. The total length is 5, so it's total length, and then we divide by the number of repeats for each of the ones that repeat factorial. So the number of repeats factorial for each of the ones that repeats. So it's what we did in the video, combinations and permutations with repeats, something like that. So if you check that, and we notice this formula right here, 5 factorial over 2 factorial times 3 factorial. It's the exact same as 5 choose 2. And so that is the number of outcomes with 2 heads, 5 choose 2. So we get 5 choose 2 divided by 32. And that gives us 10 over 32. And we can simplify that, divide both by 2. So we got 5 over 16. So now let's look at the same problem, but instead we'll consider a weighted coin. We'll still flip it five times. And this time it'll land on heads with a higher probability than 1/2. It'll be 0.7. We'll define a random variable for the number of heads. Again, we'll let it be x. And the question is to find the probability, again, that x equals 2. We'll have the same universe of outcomes. So it will be 5 tuples where each of the entries in the 5 tuple is heads or tails. The problem now is these outcomes are no longer equally likely. So we can look at, for example, the outcome tail, 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 and the outcome head, 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 head. So what's the probability of tail, 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 tail? So tails happens with probability 0.3 because it has to add to 1 with the probability of heads. And we assumed the heads was probability 0.7. So the probability of getting 5 tails, having them all be tails, each of these coin flips is independent of the others. Each of them is just a separate coin flip, no dependence on any of the other coin flips. So the probability of all of them being tails, it's going to be 0.3 to the fifth. And the probability that all of them are heads is going to be 0.7 to the fifth. So they're not equal. So 0.3 and 0.7 are not equal. And when we raise them to powers, they continue to not be equal. So we can't calculate it the same as we calculated last time. They're not equally likely outcomes. But we can still calculate it. We can just sum up the probabilities of all the outcomes where we have two heads. So two heads. So that's a head, head, tail, 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 for example. And we said there was a total of 10 of these outcomes, because that was 5 choose 2. So there was 5 choose 2 outcomes where we have two heads, because there's 5 choose 2 ways, 5 choose 2 ways to permute that sequence HHTTT. And we can look at what's the probability of getting this sequence right here, HHTTT. So the probability for that, all the coin flips are independent of each other. So we can just multiply the probabilities. So the probability of getting H on the first one, 0.7. H on the second one, 0.7. T on the third, 0.3. T on the fourth, 0.3. And T on the fifth, also 0.3. And we can write that as 0.7 squared, 0.3 cubed. And we can notice that if we permute that sequence, HHTTT at all, for example, we can look at HT, HTT. And we get the numbers in a different order. But we still get the exact same product. So we got 0.7 squared times 0.3 cubed. So we still get 2 0.7s and 3 0.3s. So when we multiply them, the product is still 0.7 squared, 0.3 cubed, regardless of how we permute the H's and the T's. So we have a total of 10 of these sequences, and each of them has probability of 0.7 squared times 0.3 cubed of happening. And we're just going to add those probabilities together. So we're really just taking the probability of each one and we're multiplying it by the total number of them. And we said that total number was 10. So we're just going to multiply this probability that we calculated by 10. So we get 10 times that probability. And remember, 10 is the same as 5 choose 2. So it's 5 choose 2 times that probability, but that's the same as 10 times that probability. And that gives us 0.1323. And I have a problem for you to think about. What's the probability for this same random variable x that x equals 4? So now we're going to move on to the second main topic of this video, which is expectation. So we'll suppose that we have a discrete random variable x, and we'll say that its values are n1, n2, n3, and so on. So this list of values is countable because x is a discrete random variable. And we'll assume that the values n1, n2, and so on occur with probabilities p1, p2, p3, and so on. And we'll assume that those are the respective probabilities. So the probability of having the value ni is equal to pi. And we're saying the probability that x equals ni is pi. So we can define the expectation of x. And the shorthand for expectation is E of x, as in this bullet. And we define it to be the sum over I of pi and I. And we're taking that sum over all possible I. So if our list of possible values is finite, then that will be a finite sum. And if the list is infinite, then that sum will be from 1 to infinity. Another name for expectation is expected value, and sometimes it's called average, although average is kind of an ambiguous term. Another ambiguous term for it is mean. Another way that we can define expected value, which is convenient for proving some things about it, is if we define S to be the space of possible outcomes and X is a discrete random variable on this space, we can define the expectation of X to be the sum over the possible outcomes in S of the probability of the outcome little s and x of s right here. This is the value of x when the outcome is little s. So we can also define the expectation this way. And sometimes we'll use one version of the expectation, sometimes we'll use the other. They're both the same. You can see that by rearranging the terms in this one and grouping the terms to get this one. So let's look at some examples. Suppose that I flip a fair coin, so not a weighted coin, a total of 5 times again. And we'll define the same random variable as last time, x, to be the total number of heads in 5 flips. And now we'll ask, what's the expectation of x? And we can calculate the expectation straight from the definition, because here we don't have that many possible values for x. So the universe of outcomes, these are going to be the 5 tuples. We'll call them A, B, C, D, E, and each of the A, B, C, D, E is heads or tails. The outcomes here are equally likely. Each of them, like we said, has probability 1 over 32, and there's 32 total outcomes here because the coin is fair. And we can just calculate the expectation then by looking at what's the probability that x takes each value. So this 1 over 32, that's the probability that x equals 0. Because we're saying there, what's the probability that we have 0 heads? So that would be probability of getting only this sequence. So t, 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 t. And that is just 1/2 to the 5th, which is 1 over 32. So we're taking the probability of getting 0, and then we're multiplying it times 0. That 5 over 32, that's going to be the probability that x equals 1. And we can look at that. We can see that x equals 1. One of the sequences is h, t, 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 t. And there's a total of 5 ways to permute the letters in that sequence because the h can be anywhere in there. And the probability of getting one of the permutations, it's going to be, so there's going to be a total of 5 of these. So we'll get 5 times 1/2 to the 5th, and that's 5 over 32. So that's why we got 5 over 32 up here next to the 1. So notice the 0 here, 0 there, 1 here, 1 here. Here, this 10 over 32, that's going to be the probability that x equals 2. So one of the sequences with x equals 2, 2 heads, it's going to be the HHTTT. And then we'll have a bunch of other sequences. We said we had a total of 10 sequences like that, which was 5 choose 2. So we got 5 choose 2. And it was times 1/2 to the 5th again. 1/2 to the 5th is the probability of each of these single outcomes. And we have a total of 5 choose 2 of these single outcomes that give us 2 heads. So 5 choose 2 times 1/2 to the 5th, and that gives us 10 over 32. This one is the probability that x equals 3. And this is going to be HHHTT and some others. And we can see that the number of those is going to be 5 factorial over 3 factorial times 2 factorial. So we get, that's 5 choose 3, which is still 10, just like 5 choose 2, and it's times 1/2 to the 5th. So we get the same thing as we got for x equals 2, so 10 over 32. And these two are also going to give us earlier numbers that we got. That's going to be probability x equals 4. And this one, this number is going to be the probability x equals 5. So x equals 4, that would be like HH, HH, T, and 5 others. X equals 5 would be HH, HH, H, and a typo there, clearly. That's better. So we get each of these probabilities, and notice the x equals 2 probability, we're multiplying that by 2. The x equals 3 probability, we're multiplying that by 3. And this arrow is pointing at this probability. The 4, we're matching that, multiplying by 4, and the 5, this probability, we're multiplying by 5. It's because when we calculate expectation, we're doing a sum over our indices I of the probability of the value times the value. So the probability for the ith value times whatever the ith value is. So each of these are, we can think of them as P0, P1, P2, P3, P4, and P5. And that P5 that I just drew, I'll put it right here. So we can think of each of those as our PIs. And this 0 is like N0, that 1 is N1. So we're saying Ni equals I here. And we can just take the sum of these numbers right here. So we can multiply each of those products and add them up, and we get exactly 2.5. So we calculated this expectation using the definition, and it gave us 2.5. So the terms in the products, they looked a lot messier than our final answer, which is interesting. So we'll see another way to get this expectation later in the video. Let's look at another example. Suppose that we flip a weighted coin 5 times. And heads will occur with probability 0.7. So tails is probability 0.3. And we'll define x to be the random variable for the number of heads. So here's a problem for you to think about. What is the expectation of x? So there's a very useful tool that helps a lot for calculating the expectation. It's going to make the calculation much simpler for a bunch of problems, as we'll see. And this tool is called Linearity of Expectation. So we suppose that x and y are random variables on the same space of outcomes. And linearity of expectation, it tells us that the expectation of x plus y is equal to the expectation of x plus the expectation of y. And we're going to look at why that's true, but we're only going to focus on it for discrete random variables because that's the focus of this video. And to prove it for discrete random variables, we're going to use the second version of the definition for expectation. So the first version we used for the problem that we did when we calculated the expectation from the definition. We use the first version of the definition where we do the sum over I of PI/NI. Now, there's another version of it that we saw on that slide where we do the sum over all of the outcomes. So let S be the space of outcomes for X and Y because they are random variables on the same space of outcomes. And we can write the expectation of X plus Y just being the sum of the random variables X and Y. So we just take the value of X, we take the value of Y, and we sum them up. And that's our random variable, X plus Y. And this X plus Y, it is a random variable. So that's why we can take its expectation. So expectation of x plus y down here, we can just write this using our second version of the expectation definition, where we do the sum over all the possible outcomes. We can write this as a sum over little s, little s being an outcome in our space of outcomes, and the sum is equal to, we write it as, so there's a missing term here, clearly. It is probability of little s times the value of x plus y when the outcome is little s. So that notation right there, x plus y of a little s, it's the same as the notation we saw on the earlier slide, x of s. And it is the value of x plus y, the random variable, x plus y, when the outcome is little s. So there, we're just using our definition of expectation. So our definition of expectation, the second definition, we just take the probability of each outcome times the value of our random variable when that outcome happens. So p of s, p of little s, times x plus y of s. And x plus y of s, we can use the definition of that. That's just the sum of the random variables x and y when the outcome is s. So that's just x of s plus y of s. So we have a p of s here times the x of s plus y of s. And we have a sum with two terms in it. We can break those terms up so we can write it as two separate sums. So here we're actually doing two steps here. So maybe I'll write this step in the middle. So we're doing a step where we write it as p of s times x of s, and then p of s times y of s. And then we are breaking up the sum. And we break up the sum into two sums, p of s xs plus p of s ys. And that gives us expectation of x plus expectation of y. So that's an easy way to see why we get linearity of expectation for discrete random variables. And there are some similar results that we can get pretty much the same way. And I'm going to move some things so that's more visible. So I'll put that up there. So here's a problem for you to prove. Prove that the expectation of c times the random variable x, where c is some constant, is equal to c times the expectation of x. And notice that if that is true, then we can say that the expectation of ax plus by, I'm only asking you to prove this for discrete random variables. So if we have some discrete random variables x and y and constants a and b, we can use what we proved in the previous bullet to write this as the expectation of ax plus the expectation of by. And using the problem that I'm asking you to do, then you can write that as a times expectation of x plus b times the expectation of y. I'm also going to ask you to take the result that we proved up there and prove a much more general result. So we proved here this result, that expectation of x plus y equals expectation of x plus expectation of y. And down here, I want you to prove the generalization of this for any k. You can assume that k is greater than or equal to 1. So we already know it's true for k equals 1 and 2. Prove that the expectation of the sum I equals 1 to k of xi is equal to the sum I equals 1 to k of the expectations of the xi's. So notice that when k equals 2, we're just saying that the expectation of x1 plus x2 equals expectation of x1 plus expectation of x2. So that's the same thing as up here. But for higher values of k, it's saying something new. I'm asking you to prove that. So that's 2 problems for you to think about. And you can use a similar method to what we did for proving it in the k equals 2 case. Similar method for this problem. And you could do a similar method for any finite value of k, but you want to combine that with some other tool that we've talked about earlier in class for this problem. So now that we have linearity of expectation, we'll assume that both of these problems that I'm assigning to you, we'll assume that the results in these problems are true. So we have linearity of expectation for any sum of random variables. And we can also put the scalar on the inside or the outside of the expectation. It won't change it. So we're going to use linearity of expectation now. And we're going to look back at one of the problems that we already did. So we flip a fair coin 5 times. Same problem we saw before. The coin is fair. And x will be the random variable for the number of heads again. And we can ask, what is the expectation of x? This time we're going to use linearity of expectation to make our calculation much simpler. We're going to define these things called indicator random variables. So I'm going to underline that word. Indicator random variables. We're going to have an indicator for each of the separate flips. So there's a total of 5 flips. So we're going to have an indicator for each flip. So x1, x2, x3, x4, and x5. Those will be our 5 indicators. And we'll define these indicators to take on values of only 1 or 0. So there'll be 1 if the ith coin flip is heads, and there'll be 0 otherwise. And we can note that our random variable x, the total number of heads, that's equal to the sum I equals 1 to 5 of xi, because each head contributes 1 to the sum, and each tail contributes 0. So the sum of these xi's, it actually counts the number of heads. It's just counting them. So x we can write as the sum of the xi's. And this is why we can do linearity of expectation using that last problem that I asked you on the last slide. So we want to calculate the expectation of each xi in order to use linearity of expectation. And we can see that each xi, it's 1 if the coin flip is heads, it's 0 otherwise. So the probability that it's 1 is 1/2. The probability that it's 0 is also 1/2. So we can write the expectation of xi as 1/2 times 0 plus 1/2 times 1. And that gives us 1/2. And that's for each I. And now we'll use linearity of expectation. So by linearity of expectation, the linearity of expectation part, this is going to be in the second step. First step, we'll write x as the sum. So x is sum I equals 1 to 5 of xi. And this is the linearity of expectation right there. So the expectation of that sum is the sum of the expectations. And each of those expectations in the sum, the EXI, is just 1/2. And we have a total of 5 terms in the sum. So we get 5 times 1/2, and this gives us 2.5. That's the same number we got last time, but this time we got it a lot more easily because we just multiplied 5 times 1/2. So linearity of expectation is pretty useful. Let's consider another example. Suppose that I roll 10 fair dice, so not weighted dice. So each side has a probability of 1/6 of landing on top. And we'll let x be the random variable for the sum of the numbers on the top of the 10 dice. So all 10 dice. And these numbers, I mean number of dots. And so we can ask, what is the expectation of x? So we'll define random variables, x1 up to x10. And these are not indicator random variables, so that's a typo. Because indicator random variables, indicator means they take on values 0 or 1. So that's an unfortunate copy-paste typo. These random variables, they're still going to be useful to us, but they're not indicators because their values are not going to be all 0s or 1s. And these random variables are going to be the numbers on the top of each of the dice. So their values can be 1, 2, 3, 4, 5, 6. And we can note that the random variable x, which is the sum of the numbers on the top of the dice, by definition, the sum of the numbers on top is the sum of these xi's, because these xi's are the numbers on top of the dice. And we're going to use linearity of expectation here, same way we did in the last slide, but here our random variables are not indicators because they're not 0 or 1. And the last slide, they were indicators. But the linearity of expectation is very similar here. So we'll first note that we already noted that x is the sum of the xi's, but we also have to calculate the expectation of each of the xi's. And to find the expectation of xi, we can just take each possible number that can land on top, each possible number of dots, and we can multiply it by the probability that that number lands on top. So we get 1/6 times 1 plus 1/6 times 2, and so on, up to 1/6 times 6. So we get 1/6 times the sum 1, 2, 3, 4, 5, 6 added together. So 1/6 times 21, and that gives us 3.5. So that's our expectation. And it's a lot easier to calculate the expectation this way than trying to calculate it using the definition. Because when we multiply by 10, we get 35. So the expectation of x, as on the last slide, we can write x as the sum. So x is the sum I equals 1 to 10 of xi. And by linearity of expectation, the expectation of the sum is the sum of the expectations. Each of those expectations we calculated to be 7/2, 3.5. So we get 10 times 3.5. We finish with 35. So the expectation of x is 35 here. So imagine if we try to calculate that with the definition. We would have had to consider all the possible values from 10. So we could have 10 as a value if we get ones on top of all the dice. And we have to consider all the way up to 6 times 10. So we get 60 there. So we'd have a lot of numbers to consider. It would be a pain to calculate the expected value that way with the definition. So using linearity of expectation, it made our calculation much simpler. So let's look at another example. So we can consider some example, like we have some sports teams. So any sport you want where you have some teams that face each other, but we'll assume that these teams are perfect, like they're robot teams, so they don't get tired, there's no injuries. And when these two teams face each other, they always have the same probabilities, same distributions. So the expected number of points for each of the teams is the same each time. So all the expectations are the same. So in particular, the expected point differential between the teams. So expected point differential, I want to clarify what that means here. So that's going to be the expectation of Team A's points minus Team B's points. So usually in sports, you want to get more points. So if Team A has an expected point differential of 5 points, then typically we're saying that they're better than Team B. And this expected point differential, we're saying that that's specifically against Team B. And we're assuming that these teams are, we'll consider them as like programs or robots. So they don't get tired, they don't get injured. The expectation stays the same for all the games they play. It never changes. We can just think of these teams as being programmed into some game, like some video game or computer game. And they're just a bunch of parameters. So we define a random variable for Team A's point differential over 20 games against Team B. So we look at what's the number of points that Team A gets, what's the number of points that Team B gets, and we do the number of points for Team A minus number of points for Team B. And we take the sum of this over all the 20 games. So we just look at what's the difference between Team A's points and Team B's points over 20 games where they play against each other. Sometimes Team B might win. So sometimes we might be adding a negative number to this sum. And we expect probably most of the time Team A is going to win. And when Team A wins, we're adding a positive number to the sum. And maybe they end up with 0 as the difference at the end. So maybe they both get the same score. So it could be some game like football where it can end in a tie. That's fine. But again, we're assuming these are not real people playing. It's just programs. So we don't have to worry about things like injuries and fatigue. So we can ask, what is the expectation of X? And we will define some random variables. Again, these are not indicators. Since they are not restricted to 0, 1. So indicators are 0 or 1. So these are just random variables, and we're going to use them in linearity of expectation. So these random variables, x1, x2, up to x20, they will be Team A's point differentials against Team B for each game. So specifically, we're going to say, and I'll write this in the margin, we're going to say that xi is defined as the number of points for the Team A minus the number of points for Team B in the ith game. So it's just that random variable. So it's just the number of points for Team A minus the number of points that Team B got in the ith game. And we have a total of 20 games. So we have an x1, x2, all the way up to x20. And this random variable we defined up here, the random variable x, this is just going to be the total point differential over the 20 games. So it's going to be the sum of the point differentials over each of the single games. So we can write it as on the last slide as the sum of the xi's. So x equals sum I equals 1 to 20 of xi. And we can also note that by the given information, the expected point differential was 5 points for each game. So that's what we're given. And that means expectation of each xi equals 5. So we can use linearity of expectation here. We can write, again, the x, we'll replace that by substitution with sum I equals 1 to 20 of xi. And the expectation of the sum is equal to the sum of the expectations. So we get 20 times 5, and that gives us 100. So you can use linearity of expectation to also do problems like this. If you know what the expectation is per event and you look at some number of events, you can find the expectation of the total just by multiplying the total number times the expectation per each one. So here the total number was 20. The expectation for each event was 5. So it was just 20 times 5. And the other problem we did previously on the last slide was really similar, the one with the dice. So there we had a total of 10 events because we had 10 dice and each one had an expectation of 3.5. So we just multiplied those two. So same method there, same method here, same method we use with the coin flips as well. And we're going to see this method a bunch more in later videos. So here's another example. Suppose that I roll 20 weighted dice now. Each dice, since it's weighted, it's going to be weighted to favor the one dot on top. So there'll be a probability of 1/2 that we get 1 on top. And all the other possibilities will split the remaining probability. So all the other possible numbers, 2, 3, 4, 5, 6, each of those will have probability of 1/10. And we'll define this random variable x to be the sum of the numbers on top of the dice. So same random variable we were looking at before. And the problem here is to find the expectation of x. And you can solve this one using similar methods to what we did on the previous ones. So that brings us to the end of this video. We will see more expectation and probabilities in the next few videos. And thanks for watching.